This video is to show you what is expected for the results as well as the discussion section for the how to write a lab report exercise. Now, the results section is really where you're going to be presenting what data you obtained. In this particular lab, the only true result we have is that the mass of our sample is 1.08 grams, and this happens to be of copper. Now, it might be good practice if you also list out your assumptions. What are we assuming about this sample? We are assuming it is pure copper, that there are no impurities. We are also assuming that each atom, each copper atom, is a sphere, a perfect sphere. We are assuming there is no empty space. Now, if you have spheres and they're rigid, then it's pretty hard not to have empty space. You have to have spheres that are flexy, that squish, in order to eliminate that empty space. So that's a really good assumption to write down. Now, in order to perform these calculations, we're going to use a technique called dimensional analysis. Now, to step back to the absolute beginning, if I have, say, a fraction, 20 over 100. A lot of us in our heads can look at this and go, yeah, okay, that's 1/5. But what are the steps you took to get there? Now, it's possible that you broke this into its component factors. So 1 times 2 times 10 over 1 times 2 times 50. And then you've canceled out that 2. And then we're left with 1 times 10. Let's break that further. And then 1 times 50. Let's break that further. 50 times, well, that would be 10. Let's break that up. And then we cancel out those common factors, and we are left with 1 over 5. Now, using that same technique, we're going to do that with our chemical quantities. And in this case, what we're going to start with is converting the radius of our copper, which is 1.96 angstroms, and we need to convert that into centimeters. Now, how do I get from angstroms to centimeters? Well, I'm going to draw a line in this particular problem-solving technique. This is called building fences. At least this is what it was called when I learned it, I don't know, donkey's years ago. So we need to be able to convert angstroms into meters. 1 meter contains 10 to the 10th angstroms. And if you don't know that, that's okay. It's part of Module 1 of General Chemistry 1. So we convert meters into angstroms. Now, I can also convert my meters into centimeters. If you know the direct conversion from centimeters to angstroms, that's fine. All you've done is gone from 20 over 100 to 1/5. With this here, I took an extra step and I broke down into other factors. That's okay. As long as we come up with the correct answer, we're okay. Now, we can double check that we have set this up properly by canceling out our units. So we have an angstrom in the numerator. We're going to cancel that with angstroms in the denominator. We have meters in the numerator. We're going to cancel that with meters in the denominator, and we're left with centimeters. So when I perform this calculation, I end up with 1.96 times 10 to the negative 8. Now, what I mean by perform this calculation is in my calculator, I'm going to punch 1.96, and then I'm going to multiply that by 100. Then I'm going to divide that by 10 raised to the 10th power. You need to understand how to work your calculator in order to get this value into your calculator. And that's part of why we're doing this exercise, because you do need to understand your calculator. So now I have the radius of one copper atom if it is a rigid sphere. So I'm going to use that radius in order to calculate the volume. So I want the volume in centimeters cubed of one atom of copper. Now, I would write that like this. So volume centimeters cubed per atom copper. So in order to do that, I need the sphere, volume of a sphere equation, 4/3 pi r cubed. Now, this is the only time in the class you're going to need this equation, so it's not like you need to write this down for anything. So we need to plug in our radius. So 4/3, the number pi, and then our radius, 1.96 times 10 to the negative 8 in centimeters, and we're going to cube that. Now again, you have to enter this into your calculator correctly, and you should get the volume of one atom of copper is 3.15 times 10 to the 23rd, negative 23rd centimeters cubed, and that is per atom of copper. So now I have the volume of an atom of copper. Now I'm going to go back and look at my sample. So I had a 1.08 gram copper sample. I was told that it has a density, copper has a density of 8.96 grams per centimeter cubed. Notice how we have centimeters cubed here and centimeters cubed up here. We want them to match. So the point, what I'm doing right now is I'm trying to find the volume of my sample. So I want to end up with those centimeters cubed. I want centimeter cubed in my numerator, and I want grams in my denominator. So when you read this value, this density value, what you're reading is 8.96 grams of copper have a volume of 1 centimeter cubed. So the 8.96 sticks with grams and the 1 sticks with centimeter cubed. So now my dimensional analysis, just to double check, I'm going to cancel out the units. I have gram in the numerator and gram in the denominator, gram of copper specifically. So they cancel out and I'm going to be left with centimeters cubed. So when I divide 1.08 by 8.96, I get a volume of 0.1205 centimeters cubed, and that is for my piece of wire. I'm just going to call it piece of copper, okay? So now I have the volume of my sample, and I have the volume of one atom. I want to find the atoms in my wire. So I want atoms in the numerator. See how I have atoms in the denominator here? And I want my piece of copper or wire in the denominator. So I'm going to start with this value, this volume of my sample, 0.1205, and that is centimeters cubed per wire of copper or piece of copper. I should be consistent, and I'm not. Sorry about that. We'll adjust. And then I'm going to use the volume of the atom of copper. I'm going to have centimeters cubed down here, and I'm going to have atoms of copper in the numerator. So now you need to make sure you understand how to read this value. Just like with the density, the way that I read this value is there are 3.15 times 10 to the negative 23rd centimeters cubed for every one atom of copper. See how the 1 stays with atoms of copper, and the 3.15 times 10 to the negative 23rd stays with centimeters cubed. This is another way to write times 10 to the negative 23rd. So now when I perform this calculation, and the calculation would be 0.1205 divided by, and then you may have to put in parentheses depending on how you're working your calculator, 3.15 times 10 to the negative 23rd, you should end up with then 3.82 times 10 to the 21st, and that is atoms of copper per piece, or per the sample, per the wire, per the piece. All of these are going to mean the same thing for our piece. Now, the point of this is we're trying to experimentally determine Avogadro's number. Avogadro's number, the theoretical Avogadro's number, and we'll need that in a minute, is 6.02 times 10 to the 23rd atoms per mole. We have atoms in our wire. What about moles? How do I find out how many moles I have? Well, I'm going to use 1.08 grams of copper. That was my sample weight, and that was per my sample, per my wire, per my piece. And I'm going to use the value on the periodic table. Now, the value on the periodic table, that is the atomic mass. That is the molar mass of one atom. And on the periodic table for copper, it is 63.546. And what that means is that 63.546 grams of copper for every 1 mole of copper. So we use this as our equivalency expression, that's what it's called, and we put the 63.546 grams of copper down here in the denominator because I want to cancel out this grams of copper, and 1 mole of copper in the numerator. When I perform this calculation, I get 0.016995, you don't round here yet, moles of copper per wire, per piece, per sample, whatever you want to call it. So now I have the number of atoms in my sample and I have the number of moles. My experimental Avogadro's number is then going to be atoms per mole, and I'm going to use these values here. So I'm going to start here, atoms, and then I will divide that value by moles here. So in your calculator, and again, you have to enter this in correctly, 3.82 times 10 to the 21st atoms divided by 0.016995, etc., which hopefully you kept in your calculator, moles, and you should get an experimental Avogadro's number with using these values here. That should end up being 2.25 times 10 to the 23rd atoms of copper per mole of copper. Now that is my experimental value. So when I'm looking over here at the percent error, I need to take 100 times, and then that straight line means the absolute value of the experimental value, 2.25 times 10 to the 23rd, minus the theoretical Avogadro's number. Theoretical Avogadro's number is 6.02 times 10 to the 23rd. So I'm going to take the absolute value of that difference. Then I'm going to divide that difference by 6.02 times 10 to the 23rd. Now, when I perform this calculation, the percent error I get is 62.6%. So that's how you go through those calculations. Now, hopefully you can pick the best title for this lab. The procedure is going to be fairly straightforward. Make sure that you write it in the third person passive objective voice. You're not going to use I, you're not going to use the researcher, you're not going to use you. Third person passive, as if magical fairies had done the lab and it just sort of happened. You're going to display results by creating a table. Now, truly the only result you have is this mass. However, it would be good practice not only to dole out the assumptions, and I'll add that back into the writing on the previous page because I think I left that out, but it would also be good practice to put all of your constants or all of the other information you're going to need. You're going to need the density. You're going to need the atomic mass. You're going to need the radius, and you're going to need to convert that radius into centimeters. So those would be good things to have as well. And then when you go to discuss it, lead me through the calculations. What was the first thing we did? Okay. The radius of copper was converted from 1.96 angstroms to 1.96 times 10 to the negative 8 centimeters. As then we used that, no, we didn't use that radius. We can't use we. The volume of one atom of copper was then assumed to be a rigid sphere using the volume equation, 4/3 times pi times 1.96 times 10 to the negative 8 cubed. The volume of one atom of copper was found to be 3.15 times 10 to the negative 23rd. I don't know. I'm just making it up as I go along. And just walk me through with words how the calculations were performed and what you did to get to where you are. Then once you get to the percent error, I need you to be able to look at this and say either that is a reasonable error based on the assumptions that were made, or could there have been some random error involved? Is this percent error unexpected or is it expected? Give me some scientific merit behind whatever opinion you offer. And then you need 2 or 3 sentences that conclude the finding of the lab. Now, in the lab report, usually when we're structuring the lab report, the abstract should come directly after the title. For this exercise, I specifically wanted to emphasize that you write the abstract last. It's written after everything is complete, but it does come first in the lab. So this is the too long, didn't read it version of the lab. And usually from the abstract, I can tell how well you have understood the exercise. Now, if you still have questions about how to do these calculations or what you may be doing wrong, please send me a message through the inbox.